Are you ready for some magic? Well, I don't have a magic wand, but I've got T1, which is almost as good. This is the episode about T1.flex, the component which allows you to instrument software dynamically while it executes from Flash. Before we come to T1.flex, I need to explain three topics: T1 scope, stopwatches, and T1 cont. While explaining these topics, I will concentrate on the difference between static instrumentation and dynamic instrumentation. By the way, T1 scope and T1 cont are dealt with in more detail in their own episodes. T1 scope functions like an oscilloscope for your software. We statically instrument tasks and interrupts to capture all events relevant for scheduling. Among these events are the transitions of the task state diagram, for example, task activation, task start, or task termination. Static instrumentation means that the source code gets modified at compile time. Obviously, static instrumentation is permanent, meaning it is always active. Our static instrumentation traces the scheduling on each core. A downloaded trace shows you what happened at runtime on the real system. So, T1 scope is what most people think of as instrumentation-based tracing. T1 is so much more than this, so much more than just T1 scope, as you will see. But let's now talk about stopwatches, the second basis for understanding T1.flex. Actually, stopwatches are rather simple. You can start and stop a T1 stopwatch at any time you like. For a static stopwatch, simply add the corresponding start and stop T1 service calls to your software, and then you will see blue boxes for this stopwatch in the T1 scope traces. The third important basis for T1.flex is T1 cont. T1 cont permanently analyzes scheduling data at runtime on the embedded target. This works without downloading any traces. T1 cont can even perform its work with no PC connected at all. Results such as min-max CPU loads, core execution times, delta times, response times, and so forth can be stored in target memory. Now that we've got the basics straight, let's look at T1.flex itself. I will connect this PowerPC based customer ECU to my PC and then show you how to use T1.flex. Here you see the T1 host software with only the project file loaded. When I now hit the link button here, the connection to the target will be established. In this case we use a CAN bus, and automatically the T1 cont table view pops up. So you see the task and interrupts, and mainly core execution times are captured here, some response times here, and so forth. And I now hit the download button, a new trace gets downloaded. So this trace now indicates the task states and interrupt states over the time axis here. And now we'll talk about T1.flex. For that, I'll switch to the symbol view, where you have a view on all the symbols. We read in the ELF file, and that's where we get all the information from. So there's thousands of functions here, because this is really a customer project. And T1.flex now allows me to instrument any function at runtime. So I can just select any function here, right click on it, and start a stopwatch on this function. What happens in the background is that the code for this function now gets instrumented to capture the start and the end of this function, and automatically a T1 cont stopwatch is set up. So when I switch to the focus view here, you see the timing parameters related to this function, which has just been instrumented on the fly. Core execution time, min, max, average, the delta time, average value for the delta time, and from these two average values we calculate the average CPU load here. It is important to note that what you've just seen is dynamic instrumentation. So we do not put static instrumentation around each function and add a little if clause which would allow us to enable and disable the instrumentation at runtime. If we did it like that, the overhead and the impact on the software would be enormous. Not so with T1.flex, which uses dynamic instrumentation. So the instrumentation gets injected while the software executes and while the ECU is fully functional. The next demonstration will prove this. This ECU uses an operating system which was delivered and linked as a library. So only object code is available, removing the option of instrumenting source code. However, with T1.flex, I don't need any source code to get an insight into any component of the software. I can, for example, select the function activate task from the list of symbols and initiate a T1.flex stopwatch on it. Activate task is an operating system service for, well, activating tasks, and we will now analyze the timing of it. Again, a second later, the most important timing parameters min, max, average core execution time, average delta time, and the average CPU load consumed by this function can be observed in the T1 host software. It is also possible to download a T1 scope trace and view the execution of the activate task function here at the bottom of the trace. Many of our customers use T1.flex for benchmarking operating systems, drivers, RTEs, and so forth. That works just fine with or without the source code. In the next demonstration, I will go into more detail, beyond the granularity of functions. If you do have the source code available, you can open it, select any code fragment, and add a T1.flex stopwatch to it. As with the previous examples, you immediately receive the most important timing parameters. Timing analysis becomes so easy with T1. With T1 scope, you analyze the scheduling, the timing on the level of tasks and interrupts. With T1.flex, you then go into detail looking at runnables, functions, or any fragment of your code. And all of this works without even stopping the software. The dynamic T1.flex instrumentation takes place on the fly. In this context, I would like to talk about how a majority of embedded software projects still analyze their timing. Not too long ago, we were called to a customer project and they were facing sporadical functional defects. They didn't really know what was going on, and to analyze the situation, they used a hardware tracer. Now, let me describe the situation that I saw when I got there. They had one single setup, and there were 40 engineers from the supplier that were forced to relocate to the OEM and sit there and analyze the problem with them in a task force. And for all these engineers, one single setup with a hardware tracer. So how did they work? Well, the hardware tracer could trace 16 seconds of embedded software execution. And all the data that was produced during those 16 seconds had to be analyzed. And that consumed around about 45 minutes. During that time, the GUI was not responding, really saying not responding. So nobody was allowed to touch the laptop, the PC during the analysis. And after these 45 minutes, you could actually start with the analysis and look at the data. In many cases, they just found out that, no, the measurement setup wasn't quite right, so we had other test conditions. Okay, we need to do it again. In the end, they were able to have and to analyze something like 8, 9, 10 traces per day. So you can imagine what they felt like when they started using T1. where they could have 8, 9, 10 measurements per minute, or even more, because they could just look here and there and go into detail here and analyze some code fragment there. So the productivity of the timing analysis really boosted up, and they were so happy with that, and in the end they were able to solve the problem. So far we've been talking about stopwatches, which represent the execution of code. But how about data and data flow? Well, T1 supports so-called data flow stopwatches. Instead of blue boxes, you will see arrows indicating the point in time when the data was sent and when it was received. This magenta colored stopwatch here was statically instrumented, so the existing code had been extended by these T1 service calls here. T1.flex also supports data flow stopwatches, which allows you to select any variable you like and get detailed timing results for those within seconds. Let me show you. From the symbol list of data objects, or using the symbol search, I now select a variable. Right-click on it and choose Start Stopwatch on Data. All read and write accesses get instrumented on the fly, just like the previously shown T1.flex features. In the focus view, there are no core execution times, of course, because we are not analyzing code execution. Instead, you see min, max, average data age. The data age describes the time difference between read and write time. Let's download a trace to get a better understanding of how the selected variable is accessed. You can nicely see it gets written to once every 10 milliseconds and read from 3 times every 10 milliseconds. Again, T1 simplifies the analysis dramatically. Synchronization problems, communication issues. With the data flow stopwatches, these become visual and thus easy to understand. This screenshot here shows what data losses look like. There are 3 data flow stopwatches, the red, the blue and the green one. Let's focus on the green one. The data gets sent by this 10 millisecond task here, but no one receives it, so it gets lost. This is indicated by a transparent arrow. At this point in time here, the done task starts to get periodically activated and receives the data indicated by a solid arrow. For some time, the 2 tasks communicate with each other and everything is fine. But look here, there seems to be a synchronization problem because the 10 millisecond task sends the data and just before the data is received, it gets sent again. Information is lost. This also works for a variable located in shared memory of a multi-core processor. Let me show you a trace you can find on our website. What you see here are 6 synchronized traces from the 6 cores of a 2nd generation AURIX processor. And these green arrows here span across the border of cores, core 0 and core 1 write to this variable and only core 1 reads from it. Understanding, debugging, profiling, optimizing, verifying the execution, the communication and the synchronization of software are the use cases we looked at so far. You can use T1.flex also for another use case, memory optimization. Some memories are small and fast, others are big and slow. Which symbols should go into the valuable small and fast memories? The figure you see here gives the answer. I took it from my book, Embedded Software Timing. T1.flex allows you to measure the access frequency of symbols. So T1.flex can tell you how frequently your functions get called and how often your variables get accessed. Moving the frequently accessed symbols to the fast memories typically offers significant potential for optimization. Let me round off this session by briefly talking about T1 measurement precision. There's a little story that comes with it. Maybe you realized that in the measurements we looked at, there were average values for delta times which were slightly below 10 milliseconds, where this should have actually been precisely 10 milliseconds. Here, for example, the delta time of a function that even has 10 milliseconds in its name. At first, I tried to ignore the problem, but then I said, wait a minute, this delta time should be exactly 10 milliseconds. So we investigated, and what we found was an operating system bug. The compare match register of the OS timer was always loaded with an off by 1 value. As a result, all the periodical task activations, they fire slightly too soon. This is not dramatic or critical, but it nicely shows how precise T1 works. I hope you enjoyed this episode about T1.flex, which did not highlight all T1.flex features. The more specialized ones will be described in separate episodes. Thank you for watching.